Last video we talked about molar mass, and we're going to kind of further that idea in talking about percent composition. So this this idea of percent composition is you could have some sort of compound, and you could ask, well, what percent by mass are the different elements, or like I'm wording this wrong, by what's like the mass percent of each element. If you have carbon, the mass of carbon in this compound, what percent does it make up of the full thing, right? If you're making a cookie, the three most common ingredients I can think of are eggs, milk, I actually have no idea, but let's just say milk. Eggs, milk, and flour. And you might want to ask, by mass, how much of this cookie that I'm eating is milk, or how much of it is flour, right? We know the recipe for this compound. We need 10 carbons, 14 hydrogens, and 1 oxygen. A lot of people are going to think, okay, well, 10 molecules of carbon, you're going to need 14 plus, of hydrogen plus 1 of oxygen. So you're going to need 25 molecules. Oh, I'll just do 10 divided by 25, right? But the thing is, the carbon is going to weigh not as much as oxygen, but more than hydrogen. So just because it's 10 over 25, which is a little bit than half of this molecule, in terms of the number of molecules, its weight, its mass is going to be a little bit larger. So it's not, it's like if I'm, my car, let's say my car is 100 pounds, and let's say I'm a crazy person and I just have my entire back seat is filled with feathers, just the entire thing filled with feathers, and then I have myself, and let's just say I weigh 90 pounds. I'm skinny, but I'm not 90 pounds skinny. Just because there are a lot more feathers in me doesn't mean it's taking up, I'm still taking up 90% of the mass, even though there's only one of me. Hopefully that makes sense. It's pretty simple to do this. I've been talking a lot, but it's really simple to do this. I know, so you could look at your periodic table for this. The mass of carbon is 12.01 U. The mass of hydrogen is 1.008 U. And then the mass of oxygen is about 16.00 U. So what we're going to do now is just kind of think, well, if I want to make 1 mole of this, I'm going to essentially find this guy's molar mass. If I had 1 mole of this molecule, well, in order to do this, I would need 10 moles of carbon, right? Remember, a mole is sort of like, it's the equivalent, not equivalent, but it's like a dozen. If I want to make a dozen cookies, and each cookie requires 10 eggs, 10 eggs. Oh, to make a dozen cookies, I would need 12 dozen eggs. Sorry, 10 dozen eggs, because each cookie needs 10, and I'm making a dozen of them. So I need 12 dozen. So remember, a U atomic mass unit is grams per mole. So, the idea is pretty simple. Oh, I'm gonna multiply by 10 moles. I'm gonna multiply by 14 moles for hydrogen and then 1 mole here, right? That way the moles cancel out and I'm left with grams, the amount of carbon in grams. So 12 times 10, that's going to be about 120.1 grams. Here, times 14, it's going to be, I'm going to use my calculator to make sure this is precise. 14 times 1.008, it's about 14.112 grams, and then this will just be 16 grams. So when I added this all up, 114 plus 112 plus 120.1. So the molar mass of this molecule is 148.324 grams. So now to find the percent composition, you don't have to overthink it. It's just going to be 120, for carbon, it's just going to be 120 over 148 multiplied by 100. So 120.1 divided by 148.324. Let me just write it down once so you kind of see what I'm doing. 120.1 over 148.324 times 100%. So that will give me about 81%. this is hopefully pretty intuitive. I can change this out for all of my elements. So instead of the 120 for carbon, if I want to find hydrogen's mass percent, I would just do 14.112 divided by 148.324. So this should be about 122. I guess I should use a decimal. Okay, so I'm going to make this 80.97. You're going to see why in a second. 148.324 times 100 is going to equal, this will be about 9.51%. And if I were to do 16 over 148 divided by 324, it's going to equal something very small. 148, about I'm a little bit, 10.79%. I think these should all add up to 100, if I'm not mistaken. Oh, I forgot to multiply by 100. Okay, wait. 10.79 plus 9.51. It's going to be probably a little off. Yeah, it's 101.27. I think it's because of rounding. I think rounding is making this the issue. Let me just check to make sure I did this correctly, just so we know. Yeah, I think I might have did some rounding here that screwed this up. These two look correct-ish. Yeah, I must have rounded this. They're getting about 150. Maybe it's 1.08 actually. That might be the problem, but I got the same thing as them. Yeah, I'll have to look back, but you know, we could see we're pretty accurate, right? I don't think we're I got this on my shirt. This seems reasonable. There's something I screwed up here. There's something. I'm not sure. I'll have to go back. Maybe the numbers I got a little bit wrong. Yeah, maybe I entered into my calculator wrong. The only difference is they have a 2. I don't know. Not going to worry about it too much because it's, reasonable. So why would we even care to find the mass percent composition? Why not just do 10 divided by 25, That was a little bit less than 50%. But as we can see, when we did the mass composition, carbon just has so much more mass than hydrogen that it basically took up 80% of the mass. Why would we care? Why is that useful information? Well, if you know the percent composition of something, you can figure out its formula, right? If you give me a cookie and if you tell me in this 100-gram cookie there are 54 grams worth of eggs, and there are 30% worth of flour, and then there's 17, that's a little bit reckless, whatever the remaining is, of milk, right? If you give me the percent composition, I could work backwards and figure out what the original recipe was. That's what I'm gonna kind of show you here. So I'll just do an example problem because it's really not that bad. White powder. Let's say we have this white powder and we run a test. So we can do this actually, believe it or not. You can cause reactions to happen, and based off it's not precipitate. What is it? There's a word. Whatever the products are, you can weigh them and you could figure out what the percent composition is. So let's say we run that on this white powder and we find out that 43.64% is phosphorus and then the rest is oxygen. And we also know that for this white powder, it has a molar mass of 283.88 grams per mole. We want to find the empirical and molecular formula. So we'll talk about the difference between those things. But essentially, we just want to find this recipe. What is this white powder made up of, and how can I make it on my own? So we're going to have to kind of run backwards. Let's be easy on ourselves. let's suppose we have 1 mole, a perfect mole of this white powder. Well, that means the mass would be 283.88 grams. So we have 2.88 grams of, we'll just call this white powder. So 283.88 grams of white powder, okay? Now, we know that in, we know that 43.64% would be phosphorus. So if I multiply this number by 43.64, and the percent means there's 436.64 grams of phosphorus for every one, percent means 400. So for every 100 grams of white powder, if you imagine, this is just multiplying by 0.4364, which you probably are used to in math class. I'm just showing you how the dimensional analysis works out. Oh, the grams of white powder are going to cancel, and I'm going to be left with grams of phosphorus. So 0.4364 times 283.88. So now I have 123.89 grams of phosphorus. Now, what I want to figure out is moles, right? I have the weight of, or I shouldn't say weight, the physics in me doesn't like that, but I'll say mass. I have the mass of the amount of eggs in my cookie. I don't care about the mass of the eggs. I want to know how many eggs. Well, I know I have the special ratio, this table of ingredients, and I know for every egg, there's 10 grams per egg, 120 grams per dozen, right? There's this ratio of egg, the amount of eggs to the weight of, or mass of eggs. Oh, I have a ratio for the grams of phosphorus to moles per phosphorus, my grams per mole in the periodic table. For phosphorus, that's 30.97. So I'm going to multiply. I know that 30.97, that just told me grams per mole. So for 1 mole, 1 mole of phosphorus, there are 30.97. 30.97 grams phosphorus. Grams of phosphorus goes away, and I just got to divide by 30, essentially. 30.97. So there's about 4 moles of phosphorus. I'm rounding here. Okay, maybe I'll do the exact for a little bit. 4.0002 moles of phosphorus. So within this 1 mole of white powder, there's about 4 moles of phosphorus. Oh, now I'm kind of getting a sense of how this formula is going to work out. But I want to figure out the oxygen. So I'm going to run the same thing. I'm going to spare some of the writing out the stoichiometry or the units to save time, but I'm doing the same thing. Instead of 43.64%, I'm going to do 100 minus 43.64, 56.36. So I'm going to do 283.88 multiply by 56.36 divided by 100, or just multiply by 0.5636, right? Multiplying it by 56.36%. So this will give me the grams of oxygen. It's about 159 grams of oxygen. So I can write this out, just 159.99 grams of oxygen. And I know, well, hey, there's a ratio. 16 grams of oxygen belongs in 1 mole of oxygen. So if I divide this number by 16, I get about 9.999673. Okay? So this will, moles of oxygen. Oh, now you can kind of see. I have 4 moles, and this is pretty much 4 moles, and this is pretty much 10 moles. So to make 1 mole, right, to make 1 mole, I would need, so let me do this. So let's do P4O10 would, that's what I have. I have 1 mole of P4O10. Or I could also say I have 2 moles. So, or I have 2 moles, 2 of P2O5. So it's either P4O10 or 2 of P2O5. That seems pretty reasonable, right? I needed 4 dozen eggs and 10 dozen cups to make a dozen cookies. Or I could just say I need, the cookie analogy starts breaking down here. Yeah, the cookie analogy would start breaking down here. Yeah, it kind of would. I guess you could think of it as, well, I could either have 4 dozen eggs and 10 dozen cups to make a dozen super big cookies, or I only need 2 dozen eggs and 5 dozen cups to make half the cookie, and then the other half to make the other half of the cookie, which would come together to form the full. And then you could call the other half its own cookie. Yeah, the analogy starts breaking down, but hopefully you can kind of understand that instead of just saying P4O10, I can just say I have 2 of P2O5. This is the empirical. Formula, the empirical formula. It's reduced ratios. Let me check the answer on this, but I'm pretty sure this seems like the correct answer. Let me find the answer. Yeah, this is the correct answer. So this would be the empirical, right? But obviously, when you add these two masses, the 123.89 plus 159.99, you get 283.88. All right? So 283.88, that's obviously what we started with. So really, yeah, it gets kind of confusing. I guess, so this is the molecular formula. But generally, we could just reduce it down to, P2O5, right? So here's, I guess, kind of what happened, the way you can kind of make sense of this result. Let me check how much time I have. This video should not be that long, but I'm probably yapping. Yikes, 18 minutes. So this is the molecular formula. This is the empirical formula. The way you can think about this is they didn't know what the formula of the white powder was, so they took this white powder, which really had maybe double of what they thought. It had double P2O5, which would give them this molar mass. But really the molar mass of P2O5 is half of that. So they're sort of, in their little box, they're shaking it and they're like, oh, I think there's 1 egg, but really there's 1 cookie, but really there's 2 cookies. They think there's 1 dozen cookies, maybe there's 2 dozen cookies. And maybe that's kind of where this discrepancy comes from. I'm just trying to make sense of the result. But hopefully this process makes sense. If you practice more and more, it's not really a process you have to memorize. I think you'll just intuitively be able to arrive at answers. So yeah, thank you for watching.